All right, ladies and gentlemen, brief discussion on carbocation stability before we move on. You do not have to hand this in. I'll start with 3 cations with 4 carbons each. Here's a carbocation. Here's another carbocation. And here's a third cation. Okay, which one of those, we'll categorize them based on primary, secondary, tertiary. You got something for the first one? Tertiary. Secondary. Primary. The carbon that is a cation has 3 bonds to carbon. That's what that means. The carbon that is a cation has 2 bonds to carbon. That's what that means. The carbon that is a cation has only 1 bond to carbon. That's what primary means. Okay? Now, when we redraw them, we have to draw them. I'm going to draw them with the proper geometry. And we got to remember hybridization if you're going to do anything about geometry. So I got a carbon with 3 sigma bonds and no lone pairs. Remember, it's sigma bonds and lone pairs for hybridization. That's it. What's your hybridization? sp2. And she gave me the name of the geometry. Not for sp2. Trigonoplanar. I thought you said that. I misheard you. Okay. So I'm going to draw it flat this way. So here we are, and it's flat. I know we usually use wedges and dashes for tetrahedral, but this is for sp2, and I wanted to do that so I could show you where the plus charge lives. Where's the plus charge? If I was a better artist, you would see that's a p orbital. I'm telling you it's a p orbital. Okay. Okay, and we got 2 CH3s out here. I'm going to draw them like this. C with an H, and there's a wedge here, and an H there. There's a C with a dashed H here, and an H here, and H here. And there's a C with an H here, and oh, you want to go wedge dash? Okay. H and a CH3. Now, if I'm lucky, which I don't think I'm going to be, I want it. I'm very happy. I want to edit it so it's the secondary one here. So this is just a CH3 over here, right? Yeah. And the secondary carbon, one of those is an H. I need my big fat eraser here. Yeah, one of those is an H. And this is just a, there, fast one on you. And over here, what do I got? CH2. We got to fix that one. There's one of the H's here. Whoa. One of the H's there. Another H here. And that group on there is an isobutyl if you want to. Yeah. C with 2 H's, followed by a C with 1 H, followed by a CH3, CH3. Not the best drawing, but there. So we good? We're good. Okay. So, once again, what's unstable about all 3 of them? What's the least stable thing about each of the 3 species here? They're all very unstable. Why? Positive charge on carbon, that's a bad thing. There's something that's even worse. How many bonds does carbon have? 3. Octet violation is the really, really bad thing. Yeah, and as a consequence, there's a plus charge. So they're related to each other. Okay, so the big thing is the octet violation. What's the only thing that can help stabilize a plus charge? Forget about anything. There's only one thing that stabilizes plus charge, period. What is it? Electron. Which of those plus charges has the most electrons with a similar orientation? That is, the p orbital I drew is the py, right? Are there any sigma bonds pointing in the same direction? Yeah? The way I drew this bond? That means this pair of electrons is sitting right beside an empty p orbital that has a negative, an overlap with that, partial overlap. That's what I'm showing there. That's called, anybody know the big word? Here's the word, fill in the middle. Anybody? A lot of science words end with that. You guys took your break very seriously, I can tell. So did I, thank you. Yeah. She knew the word. Hyperconjugation is stabilization of a cation using sigma electrons on an adjacent carbon. Should I write that down? Stabilization of a cation using sigma electrons on an adjacent carbon. There you go. And I can do it again down here. And I can do it again down here or up there. That's a lot of hyperconjugation. The only bonds that can do it on this one are this one and this one. I will remind you about sigma rotation and how this is like temporary. And the only one bond here that can help is this one. Each one of those is hyperconjugation. Which species has the most hyperconjugation? Is it the tertiary one, or the secondary one, or the primary one? Which one has the most hyperconjugation? Tertiary. So if you can make a tertiary cation, you'll form more of it. If it's possible to form a tertiary, you will form it, and you will form more of it because it's more stable. Yeah. Primary, you're going to form a lot less of. You got to use the magic hyperconjugation word. And once again, this guy down here, right now it looks like this. In a femtosecond, this thing can rotate up here, and the H got rotated here, and the other H is here. Now it's this pair of electrons that can overlap with the p orbital. Terrible drawing, sorry. Okay, so I'm talking about down here. This was pointing that direction, and after rotating, sigma rotation. The point is, if there's a carbon next door, one of the bonds is going to work. One of the bonds is going to be pointing the same direction as the empty p orbital. So you don't have to really worry about ever drawing this. I've never made a student draw these pictures. The take-home message is the important thing. Why is a tertiary carbocation more stable than a secondary? Because it's got more adjacent carbons with bonds sticking off of them that can do hyperconjugation with the empty p orbital of the carbocation. That's just words to show these pictures, people. okay? The pictures say it a lot better than all those words, I think. Don't you? That's it. Hyperconjugation.